there's a mystery woven into the fabric of reality. A connection so profound, so fundamentally strange, that even Einstein himself called it spooky. Imagine two particles, separated by the entire width of the universe, billions upon billions of light-years apart. And yet, when you measure one, the other responds. Instantly. Not at the speed of light, not through any signal we can detect, but instantaneously. This is quantum entanglement. And tonight, we drift into perhaps the strangest, most beautiful phenomenon in all of physics. Welcome back to Deep Science Talks. I'm so glad you're here for this journey. Because what we're about to explore, it challenges everything we think we know about reality, about connection, about the very nature of information itself. Let me ask you something. When you think about cause and effect, when you imagine how one thing influences another in this world, what do you picture? Perhaps you imagine touching something, pushing it, sending a signal through space that takes time to arrive. This is our classical world. The world of dominoes and billiard balls, the world where everything that happens because something else made it happen. Through contact, through force, through signals that travel at finite speeds. But in the quantum realm, the rules are different. Profoundly different. In 1935, three physicists, Einstein, Podolsky, and Rosen, wrote a paper that would haunt physics for decades. They described something impossible. They described what we now call quantum entanglement. And they used it to argue that quantum mechanics must be incomplete. Einstein was uncomfortable with this, deeply uncomfortable. He believed in what he called local realism. The idea that objects have definite properties whether we measure them or not, and that nothing can influence something else faster than light can travel between them. He called entanglement spukhafte Fernwirkung, spooky action at a distance, and for Einstein, spooky was not a compliment. But here's the remarkable thing. Einstein was wrong, not about relativity, not about the nature of light or gravity or space-time, but about this. About entanglement. Because in the decades since Einstein's death, we've proven that quantum entanglement is real. Not just theoretically real, but measurably, reproducibly, undeniably real. And tonight, we're going to understand it. Not just as an abstract concept, but as a genuine feature of our universe. We'll explore where it comes from, how it works, what it means, and why it's revolutionizing everything from computing to cryptography to our fundamental understanding of reality itself. So settle in, turn down the lights, and let's drift together into the quantum realm. To understand entanglement, we first need to understand something fundamental about the quantum world, something that defied human intuition for decades. In our everyday experience, things have properties. A ball is either red or blue. A coin shows heads or tails. You're either in the kitchen or in the living room. These properties exist whether anyone is looking or not. But in the quantum world, things are fundamentally different. An electron doesn't have a definite position until you measure it. A photon doesn't have a definite polarization until you check. These particles exist in what we call a superposition, a kind of quantum limbo, where they're in multiple states at once. Think of it like this. Imagine you have a coin spinning in the air. While it's spinning, it's neither heads nor tails. It's in motion between states. Only when it lands, only when you catch it and look, does it become one or the other. Now, quantum particles aren't exactly like spinning coins. The difference is profound. A spinning coin is actually heads or tails at every moment. We just don't know which. But a quantum particle isn't actually in any definite state until measured. It exists in a genuine superposition in all possible states simultaneously, weighted by probabilities. This is described by the wave function, a mathematical object that encodes all possible states of a system. And when you make a measurement, the wave function collapses. The superposition ends. The particle chooses, or rather, reality chooses, one definite outcome. This was proven in one of the most famous experiments in physics history, the double-slit experiment. Imagine you have a barrier with two narrow slits in it. Behind it, a screen that can detect where particles land. Now, you fire photons, tiny particles of light, one at a time towards these slits. What happens? If photons were simply particles like tiny bullets, they go through one slit or the other, and you'd see two bright bands on the screen behind the slits. But that's not what happens. Instead, you see an interference pattern. Multiple bands of light and dark. The same pattern you'd get if you sent waves through the slits. Waves that spread out, overlap, and interfere with each other. The photon, somehow, goes through both slits at once. It interferes with itself. Each individual photon exists in a superposition of going through the left slit and going through the right slit. But here's where it gets truly strange. If you try to measure which slit the photon goes through, if you put a detector at the slits to catch it in the act, the interference pattern disappears. The act of measurement, the act of observation, forces the photon to choose. The wave function collapses. The superposition ends, and the photon goes through one slit or the other, but not both. This isn't a limitation of our equipment. This isn't about being too clumsy with our measurements. This is reality. Quantum particles genuinely exist in superpositions until they're measured. Niels Bohr, one of the founding architects of quantum mechanics, tried to make sense of this. He proposed what's called the Copenhagen interpretation. In this view, quantum mechanics doesn't describe what reality is. It describes what we can know about reality. The wave function isn't a real thing. It's a mathematical tool for calculating probabilities. And measurement isn't discovering what was already there. Measurement is creating reality. Einstein hated this. He believed the moon was there when nobody looked at it. He believed in an objective reality, independent of observers. God does not play dice with the universe, he famously said. To which Bohr reportedly replied, "Stop telling God what to do." This debate, this fundamental disagreement about the nature of reality, would lead Einstein to one of his most famous thought experiments. And it's here, in this thought experiment, that quantum entanglement truly enters our story. The year is 1935. Einstein is now at Princeton, having fled Nazi Germany. He's still deeply troubled by quantum mechanics. So he teams up with two colleagues, Boris Podolsky and Nathan Rosen. to create a thought experiment that would expose what they believed was a fatal flaw in quantum theory. They published a paper with a deceptively simple question as its title: Can quantum mechanical description of physical reality be considered complete? And in this paper, they described something impossible. Something that, if quantum mechanics was correct, would have to exist, but which violated everything they believed about how the universe should work. Here's the scenario. Imagine you have two particles created together from a single source. Perhaps two photons emitted from the same atom. Due to conservation laws, these particles will be correlated. If you measure one to be spinning clockwise, the other must be spinning counterclockwise. If one is polarized vertically, the other is polarized horizontally. They're perfectly anti-correlated, like perfect opposites. Now, according to quantum mechanics, before you measure them, neither particle has a definite state. They're both in superposition. But here's the thing. They're not in superposition independently. They're in superposition together. If you measure the first particle and find it spinning clockwise, the second particle, no matter how far away it is, instantly becomes counterclockwise. Let that sink in for a moment. These particles could be separated by a light year, by a million light years, by the entire observable universe. And yet, the moment you measure one, the other knows. Not after light has had time to travel between them. Not through any signal we can detect, but instantly. Einstein, Podolsky, and Rosen saw this as proof that quantum mechanics must be incomplete. They presented two possibilities. 1. Quantum mechanics is wrong. The particles actually have definite states all along. We just don't know what they are until we measure them. There are hidden variables, deeper properties we haven't discovered yet, that determine in advance what each measurement will reveal. This would mean the universe is deterministic, just as Einstein believed. The particles aren't really influencing each other at a distance. They're just revealing information that was always there. Or 2. Quantum mechanics is right, and there really is instantaneous action at a distance. But this, they argued, is impossible. It violates the principle of locality, the idea that objects are only directly influenced by their immediate surroundings. Locality is fundamental to relativity. Nothing can travel faster than light. No information can jump instantaneously across space. And yet, entanglement seemed to require exactly that. Einstein was convinced this was a reductio ad absurdum, a proof by contradiction. Quantum mechanics predicts something impossible. Therefore, quantum mechanics must be incomplete. For nearly 30 years, this remained a philosophical debate, a thought experiment with no clear way to test it experimentally. Both sides seemed reasonable. Hidden variables seemed possible. Maybe there was a deeper layer of reality we hadn't accessed yet. Maybe particles carried secret instructions from birth, instructions that determined how they'd behave when measured. But then, in 1964, everything changed. A physicist named John Stuart Bell, working at CERN, did something remarkable. He figured out how to turn this philosophical question into an experimental one. Bell derived what's now called Bell's theorem. And what it showed was this. If hidden variables exist, if particles carry predetermined instructions about how they'll behave, then there are mathematical limits on how correlated their measurements can be. He created what's called Bell's inequality, a mathematical formula that any local hidden variable theory must obey. But quantum mechanics predicts something different. Quantum mechanics predicts correlations that violate Bell's inequality. This was groundbreaking. For the first time, someone had found a way to experimentally distinguish between Einstein's local realism and the strange non-local reality predicted by quantum mechanics. The universe could answer the question. And in the decades that followed, it did. The first experimental tests of Bell's inequality began in the 1970s. They were technically challenging, requiring precise measurements of correlated particles, measurements that had to be made quickly, before any signal could pass between them at light speed. The most famous early experiments used photons, particles of light. Scientists would take a single high-energy photon and split it into two lower-energy photons using a process called spontaneous parametric down conversion. This is a fancy way of saying they sent a photon through a special crystal, and sometimes, rarely, it would split into two photons traveling in different directions. These two photons would be entangled. Their polarizations would be correlated. Now, polarization is the direction that a light wave oscillates. Imagine a jump rope being waved up and down. That's vertical polarization. Side to side. That's horizontal polarization. For entangled photons, if you measure one to be vertically polarized, the other will be horizontally polarized. Always. Perfect anti-correlation. But here's the crucial part. You can choose to measure polarization at different angles. Not just vertical or horizontal, but at 30 degrees or 45 degrees, or any angle you choose. And Bell's theorem makes specific predictions about how often your measurements should agree or disagree, depending on what angles you choose. If hidden variables exist, quantum mechanics predicts you'll see correlations that exceed Bell's limit. Hidden variable theories predict you won't. So, which is it? In 1982, a French physicist named Alain Aspect performed what many consider the definitive test. His experiment was elegant. Two entangled photons would fly apart in opposite directions. At each end, a measurement device would randomly and rapidly switch between different polarization angles. The switching happened so fast that there wasn't enough time for any signal traveling at light speed to pass between the detectors. This closed what's called the locality loophole. The measurements were truly independent, and the results? Quantum mechanics was right. The correlations violated Bell's inequality. Significantly. Repeatedly. Hidden variables, at least local hidden variables, couldn't explain what was happening. Einstein was wrong. Now, this doesn't mean everything is determined by faster-than-light signals. That's a common misconception. Entanglement doesn't let you send messages faster than light. Here's why. When you measure your entangled particle, you get a random result. Completely random. You can't control whether you get up or down, vertical or horizontal. The correlation only appears when you and your partner compare your results later, through normal, slower-than-light communication. Only then do you see that your random results were mysteriously correlated with theirs. But you couldn't use it to send information in the moment. You couldn't encode a message, so relativity is safe. Causality is preserved. But something deeply strange is happening. The universe is non-local. There are connections, correlations, that transcend space, that exist independent of distance. Two particles can be separated by the width of a galaxy, and yet, in some profound sense, they remain one system, one unified whole. If you're enjoying this deep dive into quantum entanglement, if you're finding yourself drifting through these quantum mysteries with us, consider subscribing to Deep Science Talks. It truly helps us continue these journeys into the profound and beautiful phenomena of our universe. And if you're already here with us, thank you. Genuinely. Now, let's go deeper. Because understanding that entanglement exists is just the beginning. The real question is, how does it work? What's actually happening when two particles become entangled? To understand entanglement at a deeper level, we need to think about what quantum states really are. Remember the wave function? That mathematical object that describes all possible states of a system? For a single particle, the wave function is relatively simple. It tells you the probability of finding that particle in different places, with different properties, if you were to measure it. But for two particles, the wave function doesn't describe each particle separately. It describes the system as a whole. And here's the crucial insight. For entangled particles, their wave function cannot be separated. You cannot describe particle A independently of particle B. Their quantum states are fundamentally intertwined. Think about it like this. Imagine two dancers performing a choreographed routine. If they're dancing independently, you can describe what each dancer is doing on their own. She's spinning, he's leaping. They're separate entities doing separate things. But now imagine their dance becomes so intertwined that you can't describe one without the other. Every movement of one dancer defines and constrains the movement of the other. They're no longer separate dancers. They're a single, unified performance. This is entanglement. The particles aren't just correlated. Like two coins that happen to land on opposite sides, they're united in a single quantum state. A state that cannot be factored into particle A's state and particle B's state. Mathematically, we say the state is non-separable. Or more technically, it's not a tensor product of individual states. But what this means physically is profound. When you measure one particle, you're not just learning about that particle. You're collapsing the wave function of the entire system. The act of measurement forces the system to choose from all possible correlated states into one actual outcome. And because both particles are part of the same quantum state, when the wave function collapses, it collapses for both of them, together, as one. Now, you might be wondering, how do particles become entangled in the first place? There are several ways. The most common is through a shared origin. When two particles are created together from a single source, conservation laws ensure they'll be correlated. For example, imagine a particle at rest that decays into two particles moving in opposite directions. Conservation of momentum requires that if one particle moves left, the other must move right. Their momentums must cancel out to equal zero, the momentum of the original particle. So from the moment of creation, these particles are entangled in their momentum. They're not independently deciding which direction to go. They're created together in a single quantum state. That encodes their correlation. The same thing happens with other properties. Spin, polarization, energy. If two particles are created from a single source, and conservation laws require them to be correlated, they'll be entangled. But here's something even more fascinating. You can also entangle particles that have never interacted. This is called entanglement swapping. Imagine you have particle A entangled with particle B, and separately you have particle C entangled with particle D. If you perform a special kind of measurement on particles B and C together, something magical happens. Particles A and D, which have never been in the same place, which may have never coexisted in space, become entangled with each other. The entanglement has been swapped, transferred, moved from one pair to another. This isn't just theoretical. It's been done in laboratories around the world, and it's the basis for quantum repeaters, devices that could one day allow entanglement to be distributed across vast distances, creating a quantum internet. But we're getting ahead of ourselves. Let's return to the fundamental mystery. When you measure an entangled particle, and its partner instantly responds, what's really happening? Is there some kind of signal? Some message passing between them faster than light? The answer appears to be no. Every experiment we've done, every test we've devised, shows no sign of any signal. No energy transfer, no information carrier, nothing traveling through space. So what's happening? One way to think about it, and this is more metaphor than mechanism, is that entangled particles aren't really separate things. They're more like two parts of a single thing. Space separates them, in the classical sense. You can put them on opposite sides of the universe. But quantum mechanically, they're still one system. One unified state. Measuring one particle doesn't send a message to the other. It's more like revealing a property of the whole system. A system that includes both particles, regardless of the spatial distance between them. In recent years, scientists have created entanglement in increasingly exotic systems. Not just photons, but electrons, atoms, even molecules. They've entangled thousands of particles simultaneously, creating what's called multipartite entanglement. They've entangled the mechanical motion of two macroscopic objects, tiny diamonds, each containing trillions of atoms. They've even entangled particles in time. In these experiments, one particle is measured and destroyed. Then later, its entangled partner is created. The two particles never coexist, and yet they're correlated, entangled across time. This suggests something profound. That entanglement isn't just about space, it's about the structure of reality itself, about how quantum systems are connected, in ways that transcend our everyday notions of here and there, now and then. Now, understanding entanglement is one thing, but what can we do with it? It turns out, quite a lot. The most famous application is quantum computing. Quantum computers aren't just faster regular computers. They're fundamentally different. They exploit superposition and entanglement to perform calculations that would be impossible for classical computers. A regular computer uses bits, which are either 0 or 1. 8 bits can represent one of 256 possible numbers. But a quantum computer uses qubits, which can be in superpositions of 0 and 1. 8 qubits can represent all 256 numbers simultaneously. And here's where entanglement becomes crucial. When qubits are entangled, the quantum computer can process correlations between all these superposed states. It can explore vast numbers of possibilities in parallel. Possibilities that grow exponentially with each additional qubit. For certain problems, this provides an exponential speed-up. Problems that would take a classical computer longer than the age of the universe could potentially be solved by a quantum computer in hours or days. We're not quite there yet. Building stable, large-scale quantum computers is extraordinarily difficult. Qubits are fragile. They lose their quantum properties through a process called decoherence. But progress is accelerating. Companies and research institutions are building quantum computers with increasing numbers of qubits. And while we're still in the early stages, the potential is staggering. Another application is quantum cryptography. This uses entanglement to create absolutely secure communication. Here's how it works. Two parties, call them Alice and Bob, each receive one of a pair of entangled photons. They measure their photons, and because of entanglement, they get correlated results. These correlated results can be used as a shared secret key for encrypting and decrypting messages. But here's the beautiful part. If anyone tries to eavesdrop, if anyone tries to measure the photons in transit, they'll disturb the quantum states. The entanglement will be broken. The correlations will be disrupted. Alice and Bob will immediately know someone is listening. This isn't just harder to hack than classical encryption. It's fundamentally unhackable. The laws of physics guarantee its security. In 2016, China launched the world's first quantum communication satellite, called Meitius. This satellite can distribute entangled photons to ground stations thousands of kilometers apart, creating quantum-secured communication links across vast distances. they've successfully demonstrated quantum key distribution between Beijing and Vienna across more than 7,500 kilometers. This is the beginning of what could become a global quantum internet, a network where information is transmitted not just with classical bits, but with quantum states, where entanglement itself becomes a resource, distributed and shared across the planet. Entanglement is also revolutionizing measurement and sensing. When particles are entangled, measurements on the combined system can be more precise than any measurement on individual particles. This is called quantum metrology. For example, gravitational wave detectors like LIGO, which detect ripples in spacetime from colliding black holes, are approaching the quantum limit of measurement precision. Entangled photons, in what's called a squeezed state, can push past this limit, making the detectors even more sensitive. Atomic clocks, the most precise timekeeping devices ever created, are being improved using entangled atoms. By entangling the atoms used in the clock, scientists can reduce quantum noise and measure time with even greater precision. These clocks are so accurate that they wouldn't lose or gain a second over billions of years, over the entire age of the universe. Looking forward, quantum entanglement might revolutionize imaging. Quantum imaging techniques can create pictures with less light or reveal details that classical imaging cannot see. Imagine medical scans that require lower radiation doses, microscopes that can see biological processes without damaging living cells, telescopes that can detect distant planets with unprecedented clarity. All of this enabled by entanglement. There's even evidence that nature itself uses quantum entanglement. In photosynthesis, the process by which plants convert light into energy, there are hints of quantum effects. Energy appears to exist in a superposition of paths through the molecular machinery, exploring multiple routes simultaneously before collapsing into the most efficient pathway. Birds. Some species of birds may use quantum entanglement in their navigation. In their eyes, there are molecules that become entangled when struck by light. The Earth's magnetic field affects these entangled states differently depending on the direction, potentially giving birds a quantum compass. This is still being studied, still being debated, but if true, it means that evolution discovered quantum entanglement and put it to use long before we did. So we've seen what entanglement is, how it was discovered, how it's been tested, what we can do with it. But there's a deeper question, perhaps the most important question. What does entanglement tell us about reality itself? Remember, Einstein believed in local realism. Local, meaning things are only directly influenced by their immediate surroundings. Real, meaning objects have definite properties whether we observe them or not. This is the world that makes intuitive sense, the world we experience every day, where things are where they are, and changing them requires getting close to them, or sending something to them. But quantum entanglement forces us to give up at least one of these intuitions. Some physicists give up locality. They accept that quantum mechanics is non-local, that there are genuine correlations, connections that transcend space. But this doesn't mean faster-than-light communication. It doesn't mean causation traveling backwards in time. It means something subtler. It means the universe, at its deepest level, isn't made of separate, independent pieces. Things that were once together remain connected, not through space, pause, but through the quantum state itself, through the wave function that describes them as a unified whole. Other physicists give up realism. They argue that quantum properties aren't real until measured, that the wave function doesn't describe actual properties of objects, but rather our knowledge, our information about what we'll find when we look. In this view, entanglement isn't spooky action at a distance. It's just pause, correlation in our information. When you measure one particle, you learn something that updates what you know about the other particle. Nothing physical travels between them. Only information, in the mind of the observer, changes. Still others embrace what's called the many worlds interpretation. In this view, the wave function never collapses. Every possible outcome of every measurement actually happens. When you measure your entangled particle and get up, the universe splits. In one branch, you got up, and the other particle is down. In another branch, you got down, and the other particle is up. Entanglement, in this interpretation, is correlation across branches. In every branch where you find one result, your counterpart finds the correlated result. No collapse, no non-locality, just an ever-branching tree of parallel realities, each one as real as the others. These interpretations, these different ways of understanding quantum mechanics, all make the same experimental predictions. They agree on what we'll see when we measure. They just disagree about what's really happening, about the ultimate nature of reality. And here's the thing. We might never know which interpretation is correct, not because we lack clever enough experiments, but because their interpretations, different ways of telling the same story, different metaphysical frameworks, all consistent with the mathematics, all predicting the same observable outcomes. This is both frustrating and profound. It suggests that there may be limits to what science can tell us, not limits to what we can measure, but limits to what measurement can reveal about the underlying nature of reality. But perhaps that's okay. Perhaps what matters isn't which interpretation is true, but what entanglement reveals about the universe we inhabit. Entanglement tells us that the universe is fundamentally interconnected. That separation is, in some deep sense, an illusion. That things which seem distant and independent may be intimately related, parts of a larger whole that we're only beginning to perceive. It tells us that the universe doesn't work like a clockwork mechanism, with separate gears and springs, each doing its own thing in isolation. Instead, it's more like a symphony. Each instrument can be heard separately. Each has its own voice. But the music, the real music, emerges from their relationships, from the way they harmonize and counterpoint, from patterns that exist only in the whole, never in any single part. Perhaps entanglement is showing us something even more fundamental. Perhaps it's revealing that things, particles, objects, even us, aren't the fundamental constituents of reality. Perhaps what's fundamental are relationships, connections, correlations. Perhaps the universe, at its deepest level, is made not of stuff, but of information, of structure, of pattern. And entanglement is one of the ways these patterns manifest. One of the threads in the cosmic tapestry. Just 2 years ago, in 2022, the Nobel Prize in Physics was awarded to 3 scientists, Alain Aspect, John Clauser, and Anton Zeilinger, for their groundbreaking experiments on quantum entanglement. This wasn't just recognition of past achievements. It was acknowledgement that entanglement has moved from philosophical curiosity to the foundation of entirely new technologies. Right now, in laboratories around the world, scientists are pushing the boundaries even further. They're creating entanglement between larger and larger objects, testing the limits of quantum mechanics in the macroscopic world. They're entangling not just 2 particles, but hundreds, thousands, creating exotic states of matter with no classical analog. They're using entanglement to probe the fabric of space-time itself. There's a deep connection, still being explored, between quantum entanglement and the geometry of space-time. Some physicists believe that space-time, the very stage on which reality plays out, might emerge from quantum entanglement. That space itself might be a macroscopic manifestation of microscopic quantum correlations. If true, this would be perhaps the most profound implication of entanglement yet discovered. But for now, for today, the story of quantum entanglement continues. Every year brings new experiments, new applications, new mysteries. A new generation of physicists and engineers is building the quantum future. Quantum computers that will solve problems we can barely imagine. Quantum networks that will connect the globe in fundamentally secure ways. Quantum sensors that will reveal hidden dimensions of reality. And underlying all of it is entanglement. That spooky connection Einstein doubted, that invisible thread binding particles across the cosmos. So, we've journeyed deep tonight. From Einstein's discomfort with spooky action, to Bell's mathematical proof, to Aspect's experimental vindication, to the quantum technologies emerging today. We've seen that quantum entanglement is real, measurable, reproducible. We've seen that it challenges our deepest intuitions about reality, about locality, causation, and the nature of existence itself. And we've seen that despite decades of study, despite Nobel Prizes and technological revolutions, entanglement remains profoundly mysterious. We know that it happens. We know how to create it and measure it. But why it happens, what it really means, what it tells us about the ultimate nature of reality, those questions remain open. And perhaps that's as it should be. Science doesn't just give us answers, it gives us better questions. Quantum entanglement. This strange phenomenon that connects particles across vast distances reminds us that the universe is stranger and more beautiful than we ever imagined. It reminds us that despite our technological sophistication, despite our mathematical precision, we're still like children, peering into mysteries that stretch beyond our comprehension. And that's not a limitation, that's a gift. Because wonder, genuine wonder at the strangeness and beauty of reality, is what drives us forward. So tonight, as you drift off to sleep, remember this. Somewhere in the universe, 2 particles are connected, not through space, not through time, but through something deeper. something we're only beginning to understand. They're part of the same quantum state, the same cosmic dance. And in some strange and beautiful way, so are we all. Thank you for drifting with us tonight. Until next time, keep looking up, keep wondering, and remember, the universe is always stranger than we think.